Hi Chris, I can't hear you. Chris, can you hear me? I can't hear you. Maybe turn on your microphone.
Oh no. Well, no problem. Well, I'm not gonna record all that, so we're gonna keep going. Shows how out of touch I am with the whole workshop thing. Sorry, Zoom. Anyways, I was just touting about how cool this race car stuff is. Four parts to robots in general, right? You have your compute, which is your Raspberry Pi. You have your sensor suite, which in this case is LiDAR, IEEE, and color camera. You have your output suite, which is how the robot moves. And then finally, you have power, which a lot of people forget about because you think that you can just plug whatever you have into a wall outlet and get power there. But if your robot needs to move freely in the wild, you might want a more portable power supply. So in this case, you have actually two power sources. One power source being this 30,000 milliamp hour power bank that is strapped onto this car using a magnet. And we also have a lithium polymer battery attached to the underside of the car used for powering the car's wheels. So we separated these two power sources because it allows the Raspberry Pi and all the compute, and when you have an actual robot, all of these electrical components will fuse together and create a sort of, well, it'll draw power all from one source, and you want to make sure that that power is distributed. If you're lazy like me, you can just say, all of the compute, all of the processor logic, and all of these like sensor elements extract power from the power bank, while the motors can just have its own little power source. Because the motors will draw a lot of current, it'll use a lot of power, whereas the processor will use less power, in fact, right? Because your Raspberry Pi will draw power from the power bank in a single stream, constant 2 amps or something like that. While your motors will draw like up to 10 amps, but like only with short bursts of time. So different power supplies, but all for the same purpose of getting power to the car. You have audio on Zoom now? Just checking back in. Hide this again. Hide video panel. So RACECAR operates inside the software. We have a ROS2 stack. ROS stands for Robotic Operating System. Although we won't touch too deeply into it, the way that RACECAR is sort of built is that there are a lot of high-level functions that can grab data from sensors and do a lot of processing. And we kind of hide all of the difficult parts in the back. And ROS is one of these difficult parts, right? And ROS allows you to make a bunch of nodes and topics and connect them together sort of a way. It's like a tunnel system in the back end of the RACECAR. It allows you to drive all the sensors, data to the sensors, allows you to send all the data to the right locations. It does a lot of the hard work so that we can focus on programming the logic in the front. Again, it's very cool if you want to do all these steps and configurations for your own robot. It's just not something that we want to deal with this car right now. That takes a while. It's a long time to do everything. Okay. Oh, okay. I'm not going to go over this too much, but this is sort of like the three key things that we talk about during ROS. A node is going to be basically a script that does one of two things. You can either publish material or you can either subscribe to something. And when it publishes, you kind of get the understanding that you send something out to the world. So basically, if you have a camera node that acts as a publisher, it will publish material out to basically the void. And a subscriber node, if you have a camera subscriber node, it will basically pull that information from the publisher node. And this is sort of an example of asynchronous communication in the robot, where the publisher and subscriber don't really have a set time at which they throw stuff out or collect stuff in. It's really more of a, the publisher will do whatever it wants, but the subscriber will look for that thing that the publisher. So it's kind of like subscribing to a YouTube channel, right? A person who makes the video is the publisher node because they publish videos to YouTube. And you are the subscriber because you consume that content from YouTube. But you don't have a sort of handshake where you only will subscribe if the publisher posts the video, right? There's no sort of rule that regulates that sort of pattern. This is what it looks like inside the RACECAR. Again, all the back-end stuff that you won't have to deal with today. But everything here is just to set up what goes on in the back. So we have all the nodes on the left here. which are in charge of pulling the data from the sensor. So for example, the camera node will basically look at the camera sensor and go, I want a camera frame. And then I'm going to publish this camera frame image and IEEE stuff. Actually, this camera right here is the Intel RealSense camera, where the Intel RealSense camera combines color cameras, depth camera, and also IEEE information all in one. Fortunately, the Raspberry Pi is too weak to handle the power of a RealSense camera, so we don't use that for now. But it still has the same paradigm where everything on the left is a sensor. For example, the /joy node, all this does is it looks for the sensor. So I'm going to look for a controller. If I find the controller, I'm going to start publishing information out to the /joy topic. You can see how the /joy node points to like different nodes here. It points to a /controller node, it points to a /gamepad node, and also to a /mux node. Everything here uses the controller inputs to activate or do something. Same for LiDAR. This is what happens to the LiDAR. It publishes a bunch of scan information, basically distances around the robot, to the /scan stuff. Everything in the middle is known as a processing node. Everything in the middle will receive this information and do calculations on it to send out to the outputs, right? So after we do all those calculations, whether it's an autonomous script or a teleoperated script, when I say teleoperation, that just means I'm manually controlling the robot. Sends all the information, the signals for controlling the motors and speed, and angle out to /mux node. Now I'm going to talk about this more later, but basically the mux node will only send out the information if something happens to the controller, and this is known as a dead man switch. We don't want the race car to go rogue, essentially. We want to make sure that it always has a human ready to stop it at any time. So the /mux node will only control the outputs, basically saying if you press a button or you press a series of buttons on the controller, I will allow you to autonomously control this robot. Otherwise, will control it at all. And the idea behind dead man switch is that if you are controlling the robot autonomously and you somehow fall dead, you'll probably let go of the controller and the robot will stop moving. The robot's not going to continue moving on across the field after you die. I have a morbid example, but that's actually how it works. I have a cheat sheet for you, so we don't have to go over this information. But for working with Linux, working with command line, and working with ROS2, you'll have a bunch of commands to help you navigate through the RACECAR's library. Start some of the RACECAR features. These are alias to ROS2 launch commands. So teleop will start the RACECAR and initialize a bunch of nodes. ID LiDAR is a separate ROS2 launch command that operates and launches the LiDAR instead. The reason why we don't link these together is sometimes we don't need the LiDAR. So if you turn on the LiDAR, it's just a waste of battery. And if you use more battery by powering the LiDAR, you'll get a lot less battery when driving the car for other means. The car right now can support up to 4 hours of play before you charge either the main big battery or the smaller micro battery. If you turn on teleop, which turns on joysticks, cameras, and everything else, you will go ahead and reduce that time from 4 hours to about 3 hours. Using camera, it takes a lot of processing power to get those frames. You start the LiDAR, which you'll start a motor in the back of this module here. The motor will bring even more power and reduce your work time from 3 hours to 2 hours. So it really depends on what you turn on and what draws power from the main big battery at a time. But these are how you start the whole process system. So the start update paradigm, I'm going to just double check again to make sure I have audio. Yes, I do. Very good. Never be too careful. Oh. So the start update paradigm is how, so I guess just to poll the room, how many of you guys have worked with Arduino before? Almost all of you. Amazing. So you know what, I believe in Arduino, it's setup loop, right? Right. So this is kind of like the same thing we've mirrored this in Python, where we basically give you a template to follow, and we say the start function will only be called once at the start of the code, and this will run once, and the update function will then run again and again and again. The reason why we want an update function, or more specifically a control loop, is because we want the race car to be able to adapt to its surroundings. Right? We want this to be autonomous, so we don't want it to sort of only run once and then ignore it for the rest of the time. In order for it to be autonomous, it needs to repeatedly do calculations based on the information that it's given. which is why we need a while loop. Every single time it loops, we call that a frame. And for every frame, it will use the data collected from the sensors to run a calculation and figure out what speed and angle to command to get to the car. So I believe this flowchart explains it pretty well. We start the code using a Python 3 command, and we run through the start function here, and then goes through the update loop, and it just loops over and over and over and over again until you use Control-C to kill the program. Alternatively, it also creates another thread called update slow, which runs at 1 Hertz. And the reason why this might be useful when you're running through the actual course is because if you want to see what the race car is seeing and just print a frame out to the terminal window, it's much more efficient for the processor if you do it 1 frame a second rather than 60 frames a second. So that's why that happens. So speed and angle, again, due to accessibility and for us to make sure that high school students understand what we're saying, speed is going to be an abstract value of the car from -1 to 1. And this can be this is a float value, so it can be any value from -1 to 1, like -0.5 words out there. Oh, thank you. Oh, sorry about that. Amazing. So speed is a value from -1 to 1. Angle is also a value from -1 to 1. So for example, if you set -1 to speed, it'll go backwards at full speed. And we can toggle the speed cap inside of the ROS2 file, so we don't want it to go too fast just yet. The top speed of this car is actually around 30 miles per hour. So once you get it going, it's not going to stop. Angle, -1 represents a full turn to the left. So this car has about a 90-degree field of turn, I guess. So -1 is -45 degrees all the way to the left. 45 degrees is all the way to the right. Sorry, 1 is 45 degrees, so it's all the way to the right. And again, this is a float value, so you can assign the car any value between -1 and 1. And to understand what goes on internally, basically, it changes this value to a PWM value, which is a pulse width modulation signal. And based on that PWM value, it will change the voltage at which the car's motors are being powered. So a higher voltage would be faster, tell the car to go faster, and a lower voltage will tell the car to go slower, and vice versa for angle. Actually, it's a little different for angle because it's a servo, but you get the gist. So what we're going to do here a lot of times is we are going to enter a loop, and we're going to calculate the speed and angle values for basically what's given in a single frame, and at the end of the loop, we're going to assign that to the car. And this sort of paradigm is very useful because it simplifies a lot of things. Whenever I teach this course to high school students, they're initially very scared because the concept of autonomous robotics is kind of like challenging at first. But really, if you think about it, all you're doing is you're figuring out the right speed and angle values to send to the car after you do all these calculations, right? And this is sort of like a black box, right? You don't know what's going on here, but we know at the end of this update loop, at the end of this function, all we're doing is we're telling the race car to go at a specific command, at a specific frequency, right? So the first one is control system. If you never taken control systems, it's okay because control systems isn't really that hard until you get into like Laplace transforms. But very simply, all we're doing is this open loop feedback control is also known as teleoperation. So when we're first playing with the cars, we're going to run teleop on it. Okay. Chinese. So initially, we're going to initiate open loop feedback control using the teleop command, which will allow us to drive the car manually. Now, in the cheat sheet, I put instructions on how to drive this car manually, but it's the left bumper will allow. Left bumper is acting as a dead man switch for teleop, which means the left bumper will allow you to drive the car using these controls, I believe. The right bumper is the dead man switch for autonomous code. So once you start running autonomous code, you'll want to make sure you hold this down for anything to happen. If you don't hold this down, you're going to get confused why your code's running but the car is not. So in open loop control, what we have is a processor which takes the commands from, let's say, a controller, right? And it sends it directly to the race car. And this is a one-way street, which means everything the race car does is only going to be done if the user wants to. So, the race car has no brain. It's not going to be able to think for itself. It's only going to do whatever we tell it to do. Now, closed loop feedback control is actually what we're going to be practicing today, which, we see this extra feedback element down here, with the error calculations from the sensors. And What happens is it still requires a user input, and this is going to be a dead man switch or a failsafe. We're going to get an error signal, or actually a control output in this case. We're going to send it to the race car, and it's going to send the speed and angle to the race car. However, right before it exits the system, we have an arrow going down here, which gets error calculation from the sensor. So this is sort of like a camera here. If we're doing line following, we want to grab a frame of what the race car is seeing, and we're going to do a little bit of filtering, a little bit of algorithms to see what object is currently detected. Based on the object that is detected, then we're going to run a calculation saying which angle the car has to turn in order to get out to the line. And it's going to feed itself back into the beginning of the system. And this forms a closed loop, right? Every single frame that the race car is running the script, it's going to grab data from the sensors, it's going to send it into the system, and it's going to do this over and over and over again. What are we doing today? We're doing line following, right? So there's two parts to this that we really want to nail down before we go out and start playing with the cars. If you want to do line following, first you have to detect the line, and this is object detection. The second thing is you want to understand how to, calculate where the car should go after it detects the line, right? And that's the control system. And the two main parts, the first part is going to be our HSV portion of it, or our color detection or object detection. Now, you'll notice that this is a tape we're going to use. It's a 1-inch wide blue painter's tape. And detecting this is actually very, very simple, because it doesn't require a lot of complex object detection to do. Comparatively, if you wanted to have the race car detect a human or like a hand gesture, it would require something more difficult, much like a convolutional neural network or some other type of machine learning model, right? But for just a single block of color, we can use a technique called color image segmentation. The word segmentation just means we are going to blot out a portion of the image, and hopefully that portion of the image is our tape here. We're going to find the contour of that image, draw a line around that blob, and then find the center of it. And that way we basically just find the object without having to do any sort of complex math. Anything too complex. It's still a little bit complex, I'll show you why. So HSV is I think all of you should know what RGB is, right? RGB stands for red, green, blue. It is a color format that you can use to describe the color of a pixel on the screen. Now, RGB is great because it can describe all colors, but it's sort of hard for us to use if we want to detect a specific color, because RGB, each of these elements represents a blend of colors. So if I were to find the RGB value of, this would be easy because it's almost all blue. For example, let's say this yellow beaver on my shirt, right? It's not all red, it's not all green, it's not all blue. It has to be a combination of all of these colors. So if we want to tune this value, it's going to be a little bit difficult. It's not exactly like what this color is, unless we use like a color pair. The alternative we can use, which is like very favored in the community of computer vision, is something known as HSV. And HSV has a different color space. It still represents colors, any raw color you see in the world. It represents this in a slightly different way. So the first element is hue, which represents the raw color of the object. And if you see the bottom right corner here, I stole this image from Wikipedia, but it's a very good image for understanding how HSV works. Hue is going to be the diameter or the circumference of this shape here. So as you go around the outside border of this color wheel, you'll see you have different colors. So you see you have like red, orange, yellow, green, blue, purple, violet, and it loops back around. So everywhere, the range of hue works the same, and the scope is actually from red to purple back to red. So for example, if we set the hue to 0 to 10, that will give you a red color, regardless of what saturation value are. We're going to talk about these later. If we move up the range, so from 10 to 30, you start to get orange. From 30 to 50, we start to get yellow. From 50 to 80, we start to get green. From 90 to 110, we start to get blue. So as you go up this hue range, you'll start to detect different raw colors. Now, the reason I say raw is because we have 3 dimensions, right? We can still go into the circle or like up and down the circle. So saturation of value represents the intensity and the brightness of color. It basically just means how light or dark a color is. So if you were to basically take like the color blue of painter's tape and say which HSV values would represent this blue color, which one of these would be the best to start with, to figure out what color, which HSV color this blue tape is? And hue, right? Because hue only controls the raw color. So if we can say, like, the color of this tape is from 90 to 110 hue, right? About that range. We can perform color segmentation on it easy. We don't even have to like worry about what saturation and value are yet, because those are concerned about how light or dark the color is. Now, what makes it easier for us for detecting this blue line is that this blue painter's tape is a very vibrant color, right? Compared to like everything else in the world. Everything else in the world may be very dark and moody, but like this is a very clear and raw image. So what the strategy is to eliminate the low half of saturation value first, or to start with saturation value for tuning out everything else in the image, and then go back to hue. What do I mean by color segmentation? So we're going to have a frame. When the RACECAR detects a color frame here, what it does in color segmentation is it goes through every single pixel of this image, and it compares it to an HSV threshold that you set. Basically, you give it a lower HSV value and a higher HSV value, and any color in between, you're going to save that pixel. You're going to set that pixel to 1. Every pixel outside of that range, you're going to set to 0. Now you loop through every single pixel in an image, and it will give you back a mask. So for example, this image up here saves only the colored pixels that are orange in this image. You can see that we can map that. You run like a binary OR to map this on a main image, and then draw a contour around it. Now contours again is just a green line that surrounds an object, and of course you can find the center of it using a moment. In OpenCV, a lot of these like things that I'm talking about are like automatically done for you, so you don't have to like worry about that too much. But what you do have to worry about, and what I'm not going to give you as a solution, is this HSV threshold. So what is the lower bound and what is the upper bound that you have to set your colors to correctly save this image. And when I do the demo for you later, and I'm going to go ahead and start plugging things in because it takes some time to boost, I'll show you exactly what you have to do when you're out there to correctly save these colors and do the line fold. First of all, again, increase the low S, increase the low V, adjust the low H and high H. Of course, this probably means nothing to you, so we're going to go ahead and move on to control theory and come back to this later. This is a good slide. So in this image, what we're doing here is we're drawing this. Basically, if you have a low HSV tuple and a high HSV tuple, what you're doing is you are isolating a specific segment of this color wheel, and you're saying all of the colors inside of this segment I want to keep. Otherwise, we're just going to throw it out, right? We're going to say that's going to be 0. Okay. So let's go to controls. So now that we can detect an object, what do we have to do? We have to basically tell the RACECAR to follow the line, right? One of the hardest parts about working at any like ATR project, ATR standing for automatic target recognition, is being able to recognize the target. Because everything that succeeds with your line following begins with how well you detect the line. So when you're out there, if you don't get a good line detection, there's no way you're going to be able to tune your controls, right? Again, 2 parts of this whole lab. So bang-bang control is the first type of control we're going to be talking about, and there are 3 main states to bang-bang control. The first state is if the RACECAR is following the line, right? So if the line is in the center of the screen, that means the RACECAR is basically centered. It doesn't need to do anything else. In this case, the angle is set to 0, and the RACECAR follows this line forward. The second state is that if the RACECAR is to the left of the line, in this center image here, that means the line with respect to the camera is going to be on the right side of the screen. If the line is on the right side of the screen, then we are going to move the RACECAR to the right side. Okay, we're going to turn the wheels right because we want the RACECAR to follow the line. That makes sense so far? Great. Bang-bang is usually the easy one. The third case is if the RACECAR is on the right side of the line. If the RACECAR is on the right side of the line will appear to the left of the camera. And I get this confused sometimes too, so I'm going to fault you if you do. But in this case, we're going to turn the wheels to the left, so the RACECAR will follow the lines to the left. Right? So these are the 3 cases for bang-bang control. Now, bang-bang control, to code this up, what you do is you basically say, you're going to need a set pointer for any good control system. And your set point is what you want the car to go towards. In this case, I want the car to go towards the center, right, of the line, or follow the line. So what should my set point be? not exactly 0. So it's really easy to qualify what a set point is. You want to quantify it inside the code, right? So inside of the code, you're going to set set points equal to some value. If you want the line to be in the center of the screen, you basically set the set point to the width of the screen divided by 2, right? Because that will basically tell you where the center is. Now, in order for the race car to find out where the line is on the screen, that's going to be a separate variable, right? So once you detect the center of the line, you're going to run a calculation. You're going to say, wherever the line is, I'm going to take that point and I'm going to subtract it from the set points, right? Because if you do that, this line is, for example, at x equals 400, and the set point is at x equals 320, you're going to get an error of 120. And this error is what you use to determine which state the car should follow. So framing is just fun logic. Okay. So here's a flow chart of what background control looks like. If you want to view this later, you have the slides, I guess. But background control isn't really good, right? Because for the most part, it's a little bit inaccurate. And these race cars are a little finicky. And if they turn let's say the race car is very close to the center of the line, right? Let's say the line is just maybe 2 pixels off to the right of the car. Now the race car is going to turn right to follow that line, but it's going to turn all the way right. So it may overshoot this line. Once it overshoots, it's going to try to overshoot in the other direction again. So if you do bang bang, you're only ever sending the angle to 1, -1, or 0. And these are very severe, stark contrast angles that are really, really bad if you want to get smooth line follow. The topic is smooth here, because the smoother your line following is, the less you have to turn your car, the faster it will naturally go. So how do we fix this? So what we do is we use proportional control. And this is where I get into PID. If you know what PID is and you want to implement it in the car, you might guess. But proportional, for the most part, is good enough for a system like this that is not as sensitive. So background control is not optimal because it results in an unstable system from overcorrection. Right? So if you see the simulator here, which is why the difference is so great, you can see that the wheels of the car are really moving a lot. It's actually supposed to follow the green line, but it's actually like, over and under correcting. And in this simulation, the car is perfect. So it follows all the instructions that we give it at any point in time. The real race car is not as perfect, so it's going to be less good at following the line there. So the solution is we are going to proportionally calculate the angle that the race car should use every frame, right? So what this means is that error variable we have, the error will be calculated by subtracting the current position of the line and the set point, which is the middle of the screen. We are going to scale that to what the angle is. So if that error is very small, we are going to set the angle to a very small amount. If the angle is very large, then we're going to set the angle to a very large amount. So that's also known as a remap from like one range to another. Let's see what that looks like. This is the equation, if for those who are interested in looking at what it is. In control system, we usually represent things by these variables here. So U of t represents the control output. So this is the angle that you're sending out to the car. E of t is going to be the error. So in this case, the error is the difference between the current position of the line and the set points. And kp is a coefficient that you have to tune. So when you're writing this up inside of your program, you're going to go ahead and figure out what the value of kp is to make the system true. Although, like, in the template code I've given you, the proportional control is already programmed in. Not exactly the case for your actual lab code. So if you want to do that yourself, you can. This diagram is pretty cool, and if you use proportional control, you see it runs a lot smoother and a lot quicker, which is sort of the goal for a race, right? You can also modify different parameters like what the max speed is. You can also modify things like the turning angle, like how sensitive it is. By the way, if you have a larger kp, it's going to result in a larger turning angle. But if you have a smaller kp, it's going to result in a smaller turning angle. When you're modifying kp, you want to be careful of the saturation range, because the range of angle is only from -1 to 1. So if you multiply your error by kp and it results in an angle of over or under 1 or -1, then it's going to give you an assertion error, and you're not going to be happy. So you want to make sure that if your control output results in an angle above or under 1 or -1, you clamp it back inside of this range. Okay, we're on to line info, but I'm not going to go to this yet. I'm going to now power on the car, and show you all what actually happens when you run this code. So there are two main code snippets that I put into the system for you. It used to be 8, but I've learned from UIAC that one of these code snippets takes a really long time to get through. So these packets here, you're going to receive them when we get down there. We're going to have 5 teams, and also a cheat sheet on the other side of like all different Linux commands that you need for programming or for accessing this. There are 4 working cars, and we're going to have one team work on this car, unless one of the cars break, because car 13 has been notorious for like running into several issues. So I'm going to have this car turn on, and we're going to see what the cars look like. Oh, by the way, once you see this like welcome to RACECAR deal like screen light up, that's how you know the RACECAR is properly set up. All right. HDMI adapter. I'll run down and grab it. Everyone please hold. Thursday, Wednesday, I leave. Huh? Alright. So while I'm setting this up, do you have any questions in general of this whole system for the race? I took a look at the race track outside, it's pretty cool. It's ramps. Yeah. Alright. Wednesday was giving me so much trouble over the Alright, I don't know how this is going to work for Zoom, but
The class is over.
alright, that's going to have to be good enough.
I think it's good.
Okay, cool. So RACECAR runs in Ubuntu, which is my favorite distro for the not Raspberry Pi. Ubuntu is great in general, but once you put it on a Raspberry Pi, everything starts to break because the recommended distro for Raspberry Pi is Raspbian, which is sort of like a fork of Debian, and I don't like Debian as much as Ubuntu. For Raspberry Pi, it's a little bit better, so just keep that in mind. There's a lot of dependency conflicts when you're working with Ubuntu/Debian on the Raspberry Pi. Okay, so first things that we're going to do is we are going to check that the Wi-Fi is there, which it is apparently not. So we are going to restart the Wi-Fi. Okay, when you get your hands on this car, we're going to make sure that every team sets it up properly. First thing you're going to do is we're going to unplug the dongle because these dongles work with an AIM controller. So we need to do a fancy pairing sequence dance to make sure every team gets access to their own controller. So we're out there, we're going to get every team to unplug their controller after their car's been powered on. And we're going to plug in the controller. You know the controller is paired when you press the sender button and it vibrates. If it doesn't vibrate like that, what you're going to do is you're going to hold the pair button right next to the dongle. This is an Xbox controller. It's pretty standard, so it's going to be hopefully very familiar with something. Next thing you're going to do is the instruction manual will tell you exactly how to plug these wires in. Because it's a power bank, you need to plug these in a specific order to prevent the battery bank from browning out. Because if you plug them in all at the same time, the Raspberry Pi and the router are going to use way too much energy, and like when that happens, one of them is not going to get enough, and one of them is not going to work properly. So I think what's happening here with the router is that the router itself is not getting powered on properly due to some power issue. So look at those, it looks like it's connecting. Hopefully. There we go. Okay. All right. So the next thing you're going to do is you're going to power the car on. So again, the car has two separate batteries. One battery which you have to power on, and one battery which is like pretty violent. So the lithium polymer battery gets powered on by this button on the bottom. And when this is powered on, you'll hear two beeps. Once you hear two beeps, that means you've set this up correctly. The two beeps represent the two cells in the LiPo battery. Next thing you're going to do is you're going to open up a terminal window. Now we have these tiny little monitors for you, which is probably good for like one person to hold and tune. For the rest of you, if you want to access the code, what you're going to do is you're going to connect to the Wi-Fi on board the Raspberry Pi, and then you're going to go to the Jupyter Notebook link. And again, it's on a cheat sheet, so if you need help accessing that, we're free to help you. But if you have a computer that can access the internet, we recommend you go into the Jupyter Notebook and look at the code there, because it's a lot easier than on a tiny little monitor. The reason why we have the monitor is because the sample code that you're going to run requires a user interface to be live. If you don't have that user interface, it's going to be a little bit difficult to see what's going on. So the first thing I'm going to run is teleop, which starts the teleoperation procedure inside of the race car. You'll see this come online. You'll know it works when you see camera -6 come up and it's taking the video correctly. If it doesn't do that, what you're going to do is you're going to restart your car. Just do a sudo reboot now, and you're going to restart the car. So you heard a third beep coming from the race car. That third beep means that the drive has been calibrated and that you can start driving your car using the left dead man switch. So the joysticks will allow you to drive the car forward, backwards, and left and right. Pretty standard, right? This is like the definition of open loop control here. We're just controlling this car manually. Once that happens, if you want to see the LiDAR run, which LiDAR is not necessary for this lab, you can run YB LiDAR on a different terminal. You cannot run two processes on the same terminal, because the terminal will take control of one process. So YB LiDAR, and I'll demonstrate to you right now that this works. What this does is it will launch the ROS packet for this LiDAR, and you'll see it start spinning now. So it's going to go ahead and collect data from all around the room. If you want to see the data, there's a command on the cheat sheet to show you how. But we don't need the LiDAR for now, so I'm not going to waste electricity. I'm just going to Control-C to clear that. And then I'm going to go ahead and access the lab. So here's the part that might get difficult for a lot of us, because the labs aren't actually on the cars just yet. So I'm going to go ahead and come around while you're out there to flash the lab onto every single one of your cars. And your cars may have like different looking code just based on what the UIUC guys did, because I haven't changed it from their code yet. So if you CD into Jupyter WS, and Jupyter WS stands for Jupyter Workspace. Again, we use Jupyter Lab for this car, so if you access the code through Jupyter Lab, it's a little bit of a nicer interface, but it doesn't give you the UI. So we're going to go to student. The CD command, if those of you who are not familiar with Linux, CD means change directory, ls means list. So we're going to go into student, we're going to labs, and you should see something like this here. For those of you who have not gotten the new code, it's going to say lab 1. But if we CD into lab 2, we're going to see two files, hsvtuner.py and lab2.py. So let's go ahead and start up hsvtuner. What you're going to see is we're going to see a little bit of a user interface we've made for you to make tuning these HSV values a little bit easier. Once you see this sort of like interface start, you're going to press the start button of the controller, which will enter user program mode and bring up a few turnaround windows. So here we're going to see a taskbar, and then we're going to see a mask, and then we're going to see a color image screen of what the car is actually seeing. Okay. So what we're seeing here is the process of color image segmentation. Up here is a mask, and what we want to do is we want to do some color segmentation tuning to isolate the white parts of this image. So it makes it a little easier. I'm going to use this tape here, and I'm going to put some tape on the table so we can do some tuning. Now the hardest part about this so far, based on the track I saw, was that the difference between shade and sunlight is going to be very drastic. So tuning this color on just one part of the race is not going to be enough. You're going to have to make sure that your values work for all different parts of the race. So we can see a line here. I'm going to extend this upwards just so we can see it on the whole part of the screen. Okay. What we want to do is we want to change these settings on the left such that we can only see the blue line on the right. Right? The first thing we're going to do is we're going to modify the low and high saturation ranges, right? Because this is a dark and vibrant color. This is a raw and vibrant color compared to the rest of the surrounding environment. So to eliminate the lower half of the S values, we're going to grab this track bar and we're just going to slowly raise it. When we slowly raise it, what do we see happen in the mask? So we are eliminating a lot of the noise in the background, right? And we can clearly see the line now because it's one of the most bright and vibrant objects in the screen. Second thing we're going to do is we're going to increase the value. When we increase the value, we see a lot more stuff start to disappear, right? But if we increase it too high, the line also disappears. We want to make sure we increase to a range which is comfortable for us. Now, based on what the white parts are detecting, it's saying that this line is an object, but also the doorway is also an object, right? What do we have to do to make sure that we tell the system that only the line should be followed? I change the hue, right? Because the doorway is like an orangey yellowish color. Rather, this is a blue color. So if we increase the hue range, and the hue of blue is 90 to 110, but you can practice and change it when necessary. But if I raise this, the yellowish hue is like 10 to 20. So once I pass 20, it's going to eliminate those hues from the image. I'm going to keep going. I'm going to change this to 90, which is the known low hue for blue. I'm going to change the high hue, and I'm going to drag this down to about 110. Now, the only thing left in this image is the line, which is good. So when we press the A button on the controller, you can see the RACECAR display window on the bottom snap to this blue line, right? And when we move the car, we can now see that the RACECAR is now tracking and following the line. Now you'll notice that I see some like blue noise in, I think that's Maria's sweater, actually, which is okay. But this is something that you'll have to take account of when tuning for the race, because you don't want your race car to accidentally start seeing something else, right? Blue line is probably the most vibrant and distinctive object in the field. So you've got to account for that, and you've also got to account for that there's going to be random bits of sunlight and shade mixed in during the race. Also, there's going to be ramps. So that's the next challenge. But what you're going to do next is once you've locked in your HSV values, you can hit the right bumper switch, which again is the dead man switch for autonomous driving mode. And it's going to start turning the race car. Now, I've pre-programmed proportional control for your car here. So the car is currently on the left side of the screen, but if you look at the car's wheels, it's turning slightly left to accommodate for that. So if we place this on the floor, it's going to turn to where it's centered, right? Now, if it lies to the right side of the screen, you can see the wheels also turn to the right to try to get the race car to follow them. So the race car is currently on a little box, which is important for playing with the race car because you don't want it to go rogue. Again, it's very bad if your race car just starts driving off its own. So before you, basically you want to understand what the car is doing before you take the block off. The block isolates the wheels so the race car doesn't drive off a cliff. So again, the wheels now follow the angle at which it should to get the line back to the center of the screen. Right? So once you've gotten those HSV values, you want to write this down, because then you're going to put it inside your lab2 file. And your lab2 is sort of going to be like your, the file that you write your final code in. Because right now, the HSV thresholds, they won't save after you exit the script. So it's sort of like a one-way road. And that's it's intentional because we want you to practice writing some of this code yourself. So to look at the code, I'm going to go ahead and Control-C this. We can either open it in this app, which is known as Sublime Text. It's really nice. Or you can use Vim if you're a little bit, I'm going to say crazy, but I'm going to offend the Vim users out there. So the easiest way to, let's go ahead to see Vim HSV2.1. Vim is a text editor that is used a lot, and there's a lot of features that make it really useful. But here's the code that controls everything that you just saw. The important parts are, the most important part is the update function here. Because this update function, again, loops very, very quickly, about 60 times a second. And when it loops, it does a calculation that assigns an angle to a specific value, right? Basically, it says, if the contour exists, I'm going to set my set point to 160, because the frame itself is 320 by 240. 160 is the middle. Then I'm going to calculate my error. I'm going to say, and my error is set point minus contour center. And then I'm going to map this error to between 1 and -1 for my angle. Right? And that basically simulates proportional control. Of course, if you want to do PID, you can't use this remap function. You've got to just tune and figure out what the KP coefficient is, or KP coefficient for this race car. Okay? And at the end of the update function, we assign it to the car using this one function. The RACECAR library is built to be a little bit flexible, a little bit easy to use. Again, to hide some of the back-end code in the back. Of course, if you're very interested in looking at it, you can. It's located in the library folder. But this is just to make it easy for you to program it. So once you're done, and to exit, then you go :WQ, which is also in cheat sheet. You'll see a different file here called lab2.py. Now, once you get your HSV values tuned, once you get your controller tuned, you're going to go ahead and enter lab2.py. And then you're going to go ahead and place that value right here. Right? This might have to change to the top floor. But you're going to change this blue value to whatever you tune. And then what's going to happen is that blue value will get used in the update contour function. The update contour function is very powerful. It does all the image processing for us inside of our script. The update contour is called within update. It also works at about the same refresh rate as the update function. So it happens over and over and over again in a second. It grabs an image from the race car, that's what this line means, RC.camera.get image. And then it checks to see if the image exists. Because if the image does not exist, we don't want to do any operations on it because it'll crash our code. We just want to keep going. So if the image does not exist for whatever reason, it could be a drop packet, it could be like race car exploded, whatever happens. We're going to go ahead and, well, if the image exists, we're going to go ahead and run the code down here, which is pretty much just cropping the image so it sees the bottom half of the screen. It will go ahead and find the contours. Again, we have utility functions to help you, so you don't have to write any of this code. We can find the largest contour, again, using a utility function, and we can do contour processing. So again, contour is going to be the technical definition of it is a list of points that draw around the object you're trying to find. So if the contour exists, we're going to find the center and area on it. we're going to draw the centering area on the screen, and then we are going to show an image on the screen of what it's seeing, right? So all you have to do is change that HSV threshold, because blue is used up here, right? Blue is 0, blue 1. This is the lower threshold. This is the upper threshold. So this function is going to find all the pixels inside your frame that are between that threshold. Then what you're going to do is you're going to go to update, and inside of updates, see how inside of update contour is found. What you're going to do is you're going to finish this line, right? You're going to set angle to whatever value calculates, and that angle is going to be set equal. Or also you have to find what speed it is too, but like, you need to figure that out. And you're going to set RT to drive the set speed angle, which sends the speed and angle to the car at the end of the update function. Right? I also put some helper print statements here, so if you press the A button or the B button, it will tell you some information about the speed and angle and also the contour as well. Right? But ideally, lab2.py is what we want you to use in the final race. If you can't get there, you can just use HSV Tuner, and it will give you the solution. It's going to be quite a bad solution, by the way, because it's not your own code. It's my template code, and I always like to throw in like rocks and obstacles to prevent you from succeeding too early. But if you get the HSV Tuner working well, and you tune your system so that your car drives fast and efficiently, you can move on to lab2.py, you can save your instructions, and you can complete the race at the fastest time possible. All right? There aren't any rewards for fastest time in the race because I didn't have time to print any, unfortunately. But you'll get bragging rights for winning, being the winning team in the first ever and probably last ever MIT BWSI Thomas RACECAR Workshop in collaboration with Cal Poly Pomona Hyperloop. All right, anyone have any questions for with the demo? All right, if we're all good, I think I have stalled for long enough to where they should be ready with the cars. Again, when you're out there with your team, please start setting it up with these packets of information, but you probably won't be able to access any of the labs until I get there to flash them in. All right, so I'll do my best to get to that slowly. But until then, you can still run teleop. You can drive the car around through the race manually using the controller. Yes. So the RealSense camera requires a lot of processing power. So usually get something stronger like a Jetson, which will do the trick, or really a computer in general, right? It still works in the Raspberry Pi if you can deal with like 4 FPS. Yep. ROS 2 Iron. It's whatever the latest one it was in January. I think there's like more now. NOP, yeah. All right, let's go ahead and, oh, one last thing. If you do need to reboot, I'll go ahead and teach some commands really quickly. Never, ever, 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 ever unplug the power from a Raspberry Pi while any process is running or in general. Reason being, you might accidentally corrupt the Raspberry Pi and it can never be recovered. So if you ever want to shut down the Raspberry Pi or reboot it, don't pull out the power, right? Run one of these two commands. So the first command is sudo shutdown now. And I'll ask you for a password, but sudo shutdown now will safely close all the processes on the Pi so that if nothing is left open while you close it down. If something's left open, then some bits can be swapped and it just corrupts the entire disk, right? The password is RACECAR at MIT, also on the cheat sheet. Other command, if your internet is still not working and being a little wonky, is sudo reboot now. Sudo reboot now just restarts the Pi, right? But after you're done working with the car, please do not plug out the power. Please run sudo shutdown now. Type in the password RACECAR at MIT. It's going to close down. Once it closes down, you're going to wait 30 seconds. 30 seconds is sort of the amount of time before doing anything else. Because while it's shutting down, it's going to go through all the processes to make sure that everything is safely closed. Once 30 seconds have been over, you can unplug it. All right? Okay, cool. Everyone ready? All right, great. Let's hit the field.
but they had a lot of issues with fusion
I mean, if we could do that shitty.
yeah, I mean, like I said, with this, it's kind of relevant. Unless you get a
Well, I
they had
no, that is the best. That is the. No, no, no.